Projectile motion for Physics 1 Georgia Tech. The introduction purpose of the lab was to study the motion of a paper ball representing a projectile with experimental and computational models, also to determine what would happen when drag force is present versus absent. Here are some models and fundamental physics principles used. The Newton's second law momentum principle pertains to net interactions between our system, which is the paper ball, and surroundings, so our net force, and how this relates to changes in momentum of the system. And the formula is change in momentum over change in time. The position update formula measures two positions and allows us to determine the average velocity for an object during a time interval. So the formula is position final equals position initial plus v average delta t. And velocity update formula predicts the velocity at some time later. So v final equals v initial plus f net over mass times delta t. Additional physics principles are the drag force, which is a force that acts against motion of a paper ball, and when air resistance is accounted for, drag force needs to be incorporated into the equation, and it affects both the x and y direction of projectiles, and the constant b is a proportionality constant based on experimental data. Also, gravitational force is a force of gravity given by mg and is pointing the negative y direction, as you can see in the formula. A brief preview is our computational model that included drag was more accurate to the experimental data than the model that did not include drag force. The experimental setup shows the paper ball, which is our system, surroundings, which is gravity and the hand throwing the paper ball, as well as air resistance, the experimental model, which was tracker, and then the computational coding model was GlowScript. The procedure is record a video of a loose paper ball being thrown as a projectile, insert the video into tracker or experimental model, use GlowScript, the computational model, to add drag force and control proportionality constant b, and plot the data all into Excel and compare results. Here's our tracker data. As you can see, our initial times, our x initial, and then our y initial. And then we analyzed tracker to get initial conditions and then made two models to compare results to, one that included the effective drag and one that did not include the effective drag and only gravity. And here's our GlowScript, and here's the ball's mass, 0.005, and here's our position velocity update formulas. Here's g equals 9.8, here's our proportionality constant, and when v is equal to 0, the F net is the only force of gravity and is not accounting for the drag force. And here's our F net and then our updated velocity and position update formulas. Here's the GlowScript continued. Here's a model when drag force was applied versus no drag force being applied. And here's the similarities and differences. The Y tracker is the blue line, the red is the Y with gravity involved, and then the yellow is drag and gravity. And as you can see, it examines the effect of drag of different trajectories, and the tracker data is more similar to the data that includes the drag and the gravitational forces, meaning that it's more accurate to the data that we observed in class when drag is present. Possible sources of error include when we were setting up the iPad, we could have had human error when we were trying to account for the motion of the paper ball, and that could lead to tracker errors and position and calculation errors overall. What does it mean and what if? Neither model predicts terminal velocity. An experiment to find terminal velocity of a paper ball would be allowing the ball to drop from higher so the drag force can grow more to equal gravity. And experiment dropping from a tall height could allow us to see when velocity stops increasing and to find the maximum falling speed. And when thrown straight up, the paper ball has to rise and then fall back down, and air resistance will slow this process so it stays in the air longer when compared to being thrown at an angle. Conclusions are when b equals 0.001, so drag force is accounted for, the computational model is more accurate to the experimental data, and drag force did demonstrate an effect on projectile motion.